This is the video that I was telling you, or the problem that I was telling you, is kind of the opposite of a sticky collision. So in this one, we have an astronaut at rest in space. So you're in space, you know, you have no friction. So most all of these will be on ice or in space or on a slippery surface, something to where you don't have to deal with friction. In space, fires a thruster pistol that expels 35 grams of hot gas at 875 meters per second. The combined mass of the astronaut and the pistol is 84 kilograms. How fast and in what direction is the astronaut moving after firing the pistol? So let's write down what we know. We know that our initial velocity for both is 0 because the gas is at rest in the beginning and so is the astronaut. So that's the initial velocity of A and B. I'll write that so you know. Then we have the mass of B is 35 grams. And we're going to need to convert this to kilograms because we can't have grams and kilograms in our problem. We need to have everything in kilograms. And then we have the mass, or the final speed of the air. And again, you can use whatever letters you want. If you want to call the astronaut A and the gas G, I mean, you can do whatever you want. The letters don't really change anything about your problem. I just like using A and B because it's easy. Then you have the mass of the astronaut and the pistol. So I'm going to call that MA. And then we want to know the final velocity of the astronaut. Okay, so we're going to do the exact same thing. Okay, we'll write the initial velocity of the astronaut, or the initial momentum, sorry, of the astronaut plus the initial momentum of the air is equal to the final momentum of the astronaut plus the final momentum of the air. Okay, so then we'll have the same thing. We'll have the mass of A plus the initial velocity plus the mass of B times the initial velocity. And you see these two initial velocities are the same. So this is kind of the opposite of a sticky collision problem. We have the mass of the astronaut times the final velocity of the astronaut plus the mass of the air times the final velocity of the air. Okay, so now we can go ahead and we can put numbers in for this. So our astronaut is 84 kilograms and his initial velocity is 0. So that will cross out. And then we have the initial, or the mass, excuse me, of our air times the initial velocity of the air. That 2 will cross out. Then we have the mass of the astronaut times his final velocity plus the mass of the air, hopefully I can fit this, times the velocity of the air. Okay, so on this side we'll just have 0 is equal to 84 kilograms times VFA the final velocity of our astronaut, plus, and I'm going to multiply these two, and I'm going to get 30.625 kilograms times meters per second. Okay, now something I should have thought about here is the astronaut is going in the opposite direction of the air. So if we want the astronaut's direction to be positive, we actually need this direction to be negative. Okay, which will then make this negative as well. Okay, because they're going in opposite directions. So if this is negative, then we can add 30.625 kilograms times meters per second. And you could have left it positive, that would be completely fine, and you'd end up with a negative velocity, and that's just saying that your bullet's going in one direction and your astronaut's going in the other. So that's why you would get those two different signs. It's either way. I just like to have the astronaut being positive. So I added 30.625 kilograms times meters per second, which is a momentum, to both sides. And now I have 84 kilograms times VFA on the right side. To get this final velocity by himself, I'm going to divide both sides by 84 kilograms. Okay, and then you end up with 0.36 meters per second. Again, if you had left it positive, you would have gotten the exact same answer. It would just be negative. That's the only difference. So our astronaut will be moving in the opposite direction of the air at this speed. Hopefully he's moving towards his spaceship and not away from his spaceship, or else he will float away into outer space because there's no way for him to stop.